Hi everybody, welcome back. We're going to finish, hopefully finish the integral test, section 9.3 today. But first, as I mentioned, I made a mistake at the end of the last video. I wanted to show 1 over n factorial converges. And in order to do that, I pointed out n factorial was 1 times 2 times 3. And now here's where I made a mistake. I put the wrong, and this is strictly greater than a function I'm going to make up, which is 1 times 2 times 2 times 2, and this would be 2 to the n minus 1. It's greater than, because here I'm multiplying by 3, I'm multiplying by 4, here I made just 2's. So if that's true, then here's my second mistake, then the 1 over n factorial is strictly less than 1 over 2 to the n minus 1. And these are the mistakes I made. They are right now, and I knew it. I was standing there watching. I think it's because the dog was barking. I'm not sure. But so then we showed that if this series, 2 to the n minus 1, if that converges, then because that's the bigger series, so does the factorial. And it does. This converges. Let's see. The partial sums is a minus 1 over r. This is a geometric sequence. A is what, 1, and r is a half. And 2 converges to 2. We're not saying that this series here converges to 2. We're just saying there is an upper bound for that series. It will never, ever go past 2. So because this one converges, and because it's strictly greater than from the comparison test, then that one absolutely has to converge. So I apologize about having to go over that again. Let's do that theorem over here. It's called the integral test. Quite a powerful test. Poof. And it just says simply a series of non-negative terms converges if whoops, that's the wrong thing. Let f be a continuous, positive, non-increasing function. Continuous. These are the three assumptions we made yesterday. Continuous, positive, non-increasing. Function. Notice we're not really talking about series right now. We're back to functions. And suppose that a sequence of a sub k's is the exact same as f at x sub k. We're saying this is a function. It's continuous. Function, something look like that. And what this statement here is saying is that every time we have an a, they correspond. So this is just integers, and it says f at those integers, they're correspondent. If that's the case, then the series converges. If and only if the integral from 1 to, this is 1 to infinity. The series converges if and only if the integral of f at x from 1 to infinity converges. One diverges, the other diverges, and conversely divergent. Very important, powerful result for us. It's called the integral test. And let's just do a couple examples, I guess. How about investigate convergence of... Come on. Investigate convergence. Oh, man. Example, how about from k equals 1 to infinity of, how about 3 over k plus 2 squared. Excuse me. We're going to investigate the convergence of that. By the way, the sequence a sub k, it looks like this: 3/9, 3/16, 3/25, 3/36. That's the sequence, and the series now we're adding them up. And we're just investigating whether, when we add up all these things ad infinitum, it converges. So that's what we're doing, and all we're doing is test convergence. The sum of this, well, we need some more tools for that when we talk about the sum. But all we're doing is test convergence. So we need to integrate from 1 to infinity of 3 over x plus 2 squared dx. Excuse me. This definite integral, if we take the derivative of this, it's negative 3 over x plus 2 to the first power, and we're going from 1 to infinity, which is, let's see, negative 3 over, that's 0. The limit as this goes to infinity, the denominator is getting big, then it's minus negative. The definite integral converges. The definite integral converges, and not only that, the area under the curve of this definite integral from 1 to infinity is 3. That's not to say, incidentally, that this series is going to add up to 3. All it's saying is because the definite integral converges, the series converges. How about another example? Over here. Of one that doesn't. Let's k over k squared. Let's examine this. I think. Yes. The convergence of this, k to 1 to infinity, of course. Investigate the convergence. That's another k. Sorry about that. Of that. So what we're going to do is integrate. And make it a definite integral from 1 to infinity. If we integrate this thing, remember we have to use a u substitution, let u be the bottom, and dk. Sorry, this is dx. These are all x's, sorry. Because we invented a function called it. So we're going to integrate that, and that's the ln, right? Where the heck's the integration? And if we integrate that, it's 1/2 ln of x squared plus 3 from 1 to infinity. If I chuck an infinity in here, it goes off, it diverges. Thus, the series diverges. How about p's? How about p series? Shall we do that? 8 minutes and 20. Yeah, let's try it. Just stop it. I would really like to get this one in. P series. Convergence of P series. And so first off, let's define what a P series is. A P series is a series of this form. And we want to investigate the convergence, divergence of this. We can also write it by k to the negative p if we want, k to 1 to infinity. We want to investigate the convergence or divergence of this. Please note, if p equals 1, it's the harmonic series, which diverges. So we want to investigate if p doesn't equal 1. So suppose p doesn't equal 1. Then the series converges if x to the negative p dx converges. If that converges, the whole series converges. And so we're going to integrate. I have 9/16. Whoops. And we're going to integrate this thing. And in order to do that, well, let's see. This would be x to the 1 minus p over 1 minus p. There we go. That's the integrating. And then I'm taking this from 1 to infinity. Minus 1, x to 1, yeah. Which is, x to 1 minus p over 1 minus p minus 1 over 1 minus p. And I'm suggesting this part right here. Note, x to 1 minus p converges if p is less than 1. X to the 1 minus p, suppose that's less than 1. Suppose that's a half. 1 minus a half, x to the half. That'll converge. If p is greater than 1, this x to the 1 minus p diverges. So there's a theorem over here, a p series will converge, if and only if p is less than 1. Otherwise diverges. Okay, that's a long one. I hope that works. Stop that. Over.